All right, I'm recording now. Okay, so we have 2.3 basic differentiation. So we get to learn these shortcuts today. Yay, we made it, right? So the derivative, we've seen the notation before, can be given as f prime of x, y prime, dy over dx, or dy over dx. All of these notations represent the derivative of our function at x. Okay. So with that being said, we come to our first rule for derivatives, and it is the derivative of a constant function. So if f of x equals some constant c, then that derivative of a constant will always be 0. So remember, a constant is just a number without a variable. So the derivative of any constant is 0. And the reason for that is, well, remember, that derivative is just a fancy word for slope. So let's say I was given the function y equals 5. That would be the graph of a horizontal line. And what is the slope of all horizontal lines?
0.
0. So again, when you take the derivative, you are just getting the slope for that function. Crazy, right? Okay. So let's go ahead and try out our derivatives. Example 1, y equals -5. So we'll take the derivative, we'll say y prime, and what is the derivative of -5?
0.
0. Look at that. Now we have y equals pi, and guess what? Pi is a constant. So what is the derivative of pi going to be?
0.
0. Oh, that's so easy. Calculus is so easy now, right? No, not yet.
Calculus.
Calculus. Okay, so that's your first derivative rule. That is the derivative of constants. If you ever give a constant, it's always going to be 0. Okay. Next is the derivative of a power function. This is your best friend for derivatives. So if you're ever given a power function, x to the n, where n is any real number, then the derivative of x to the n is going to be given by n times x to the n minus 1. So all we do is we take this power, we bring it down, and we subtract 1. And that is the power rule for derivatives. That is your best friend from here on out for derivatives, of course. And then the derivative of x is just going to be 1. So if we explored that, if I said d over dx of x, the power of this x is 1. And if we use the power rule, you'd get 1 times x to the 1 minus 1, which would give me 1x to the 0th. And what is any number raised to the 0th power?
1.
1. So this would just become 1. There you go. So that's why the derivative of any variable by itself, any single variable to the first power, any linear variable, I guess you could say, would always be 1. Okay, let's go ahead and try out the power rule on these functions. So 3 says, what is the derivative of x to the 5th? So if we take the derivative, what number's coming down?
5.
5. You get 5x, and what's my new power?
4.
That's it, guys. That was nice, huh? Now remember, before the test, you had to do x plus h. Imagine plugging that in and distribute it 5 times. Anybody want to do that?
Can Ryan show us?
Yeah, Ryan. Good.
Wait, what? Huh?
You're gonna distribute x plus h to the fifth.
I'll mute
Nope.
myself again later.
Okay, let's try it again. Y equals x to the 30th. We're going to take the derivative. And what is the derivative of x to the 30th? What do we have?
30x to the power 29.
That's it. Now imagine putting x plus h in that one. You'd have to distribute that 30 times.
Wow.
That'd be the worst. Okay. 5. Y equals 1 over x cubed. Okay, we cannot take the derivative in this form. So we have to rewrite it algebraically. So when we rewrite this algebraically, this just becomes y equals x to the negative 3. Here we use the negative exponent rule. So this used x to the negative n, which is equal to 1 over x to the n. And it puts it into the proper form for us to take the derivative. Okay, and playing with notations, I'll just say dy over dx is equal to, and now what's the derivative of x to the negative 3?
Is it negative 3x to the negative 4th?
Very good. Now, what would be another way to rewrite this?
Negative 3 over x to the 4.
There you go. Sure, this is okay, but this one's way better. Okay, excellent. Number 6. This says d over dx of x to the 5/3. So all this says is take the derivative of x, or the derivative with respect to x. So it's already set up. And what number is coming down?
5/3.
5/3. 5/3 x. You take 1 away from 5/3, and what does that leave us with?
2/3?
There you go. All right. Any questions so far on these examples? We like derivatives now, right? Okay. Number 7. D over dx of the square root of x. We cannot take the square root in, we cannot take the derivative in this form. So we have to rewrite this. So we're going to rewrite this as d over dx of x to what power?
1/2.
There you go. Good. So we just rewrite from radical to rational exponent. And this puts it in the proper form so we can take the derivative. And that means what number is coming down?
1/2.
1/2 x to the what power?
Negative 1/2.
Negative 1/2. Now that's a cool answer, but what's another way to rewrite this?
One half over x to the 1 over 2.
1 over 2x to the 1/2, right?
Yes, my bad.
And again, I think it would take that answer, but you could always rewrite it back as just 1 over 2 square root of x. And don't even worry about rationalizing that. You don't have to. All right. Those are derivatives by the power rule. Do we have more on the next page? Yeah, when we get there. All right. Any questions on those ones? Everybody good?
Wait, I have a question. Sorry, I couldn't hit the mute. So for number 6,
Uh-huh.
where it's got the fraction in the exponent, it's okay to leave it like that. Just if it's a negative, it would be preferred. Well, you would need to write it in the other form, 1 over.
Exactly. But I mean,
Okay.
if you want, it's good practice to rewrite them. So if you want, you could have had this as 5/3 times what?
The square root of x to the third, or is it the cubic root of x
Cube
squared?
root of
Cube root
x
of
squared.
x squared.
There you go. No, so it's always good practice and good habit to know how to rewrite these algebraically. So
Okay.
no, not a bad question.
I mean, they're all good questions, right?
Right? Great. I should have said that was a good question. But maybe I got terrible questions today. All right. From my earlier classes. All right. The next rule for derivatives is called the constant multiple property. Basically saying if you have a coefficient or a constant in front of your function, then just move that constant to the side and take the derivative of your function. And then when it's done, multiply your constant back in. So that kind of follows the limit properties that we had. Remember, if we had the limit as x approached some number, let's just say a 5x, we could take that 5 and move it to the front. So these limit properties have, and the derivative properties are similar. Okay. All right. So let's just go ahead and try out that constant multiple property above. So here we have d over dx of 3x to the 4th. So what we're going to do is that by the constant multiple property, I'm going to rewrite this as 3 times d over dx of x to the 4th. So we isolate the function that we want to take the derivative of. And now what is the derivative of x to the 4th? Anybody?
4x to the third.
4x
Sorry.
to the third. And then multiply them together, and we get 12x cubed. So the constant multiple property just allows us to split terms up, but we honestly don't really have to use it unless we need to. We could have just said, hey, I'll rewrite this. We could have just said, hey, this 4 will come and multiply that 3, giving me 12, and we were done a long time ago. Very nice, right? Multiply to 12, take 1 away, and it's done. Okay. Here, again, just to practice our constant multiple property, I'll take out the -1, and you'll have d over dx of x. And if you remember the first page, what is the derivative of x?
It was 1.
It was just 1. So here we get -1. All right, that's the constant multiple property. Any questions on that? Okay. And another property or rule for derivatives is the sum and difference properties. So remember, just like limits, if you had multiple terms, you could apply the limit to multiple terms. The same could be said for the derivative. Here you have d over dx of f of x plus or minus g of x. So however many terms are connected by addition or subtraction, we can apply the derivative to them separately. We can say, all right, the d over dx of f of x plus or minus d over dx of g of x, and so on and so forth for however many terms you have. So this just says, hey, apply the derivative to all these functions. Okay, so I'm assuming we're experts at derivatives now. So for number 10, let's go ahead and find the derivative of this expression. So let's just get started already. No holding back. What's the derivative of x to the 8th?
8x to the 7th.
8x to the 7th. Plus, what is the derivative of 12x to the 5th?
60x to the 4th.
There you go. Minus, what's the derivative of 4x to the 4th?
16x to the 3rd.
Good. Plus, what's the derivative of 10x cubed?
30x squared.
30x squared. What is the derivative of negative 6x?
-6.
There you go. And what's the derivative of 5?
0.
0. Look at that. Oops. That wasn't bad at all, huh?
I'm waiting for the hard stuff.
Oh, there's nothing hard today. We just made your life simpler. All right. So the shortcut derivatives make our process a lot simpler. Okay, example 5. Find the points on the curve y equals x to the 4th minus 6x squared plus 4, where the tangent line is horizontal. All right. Horizontal tangents occur where the derivative is 0. Well, if you think about it, so if you look for a horizontal tangent line, or if you look for any horizontal line, what is the slope of any horizontal line?
0.
0. So if we're looking for where a horizontal tangent line will occur, this means we're going to take the derivative and set it equal to what number?
0.
0. That's it. And of course, I'll draw you a picture when we do it. So here, let's take the derivative of that function, and I'll just say y prime. And what is the derivative of x to the 4th?
4x cubed.
Good. 4x cubed minus, what is the derivative of 6x squared?
-12x.
Good. And what's the derivative of 4?
0.
0. Excellent. So there's our derivative. And now, again, if we want to find out where horizontal tangents occur, we're going to take our derivative and set it equal to 0. So I'll say y prime equals 0. And we get 4x cubed minus 12x equal to 0. And now let's go ahead and solve for x. And what could I factor out here?
4x.
4x. That'll leave me with x squared minus
3, sorry.
3. And then if we solve for x, what are my 3x values going to be?
0 and plus or minus square root of 3.
Good. 0 and plus or minus the square root of 3. Okay. So what we're saying is that when x is 0 and when x is the positive or negative square root of 3, we are going to have a horizontal tangent line whose slope is what?
0.
0, right? And it said find the points. So what we're going to do now is take these values of x and plug them into the original function for x. So now we're looking for the points. I'll just write them here. X equals 0, x equals the square root of 3, and x equals the negative square root of 3. And y equals, y equals, y equals. And first one's easy. If you plug 0 into the function above, we're going to get what?
4.
4. That one's nice. Now we have to plug in the square root of 3 and the negative square root of 3. And actually, I'm going to use Desmos just to show you what we're finding. Again, I don't like to make it seem like we're just crunching numbers, which we are, but there's more of a reason to what we're doing. Okay. Get out of here. There we go. All right, first I'll type this in. X to the 4th minus 6x squared plus 4. And then here, actually, what's that going to give me? Yeah, that's going to give me everything I need. So if you typed in the square root of 3 and the negative square root of 3, you should have came out with negative 5 and actually, yeah, they're both negative 5 and negative 5. So from our graph, you see on the left, at those points here, I'll put my sketch over here. So we look something like looks exactly like the one on the left, okay? All right. So what we're saying is that at these points that we just found, we have horizontal tangent lines. So at this point, you would have a horizontal tangent line. At this point, you would have a horizontal tangent line. And at this point, you would also have a horizontal tangent line, which all of these have a slope of 0. That's pretty cool, huh? Yeah, it's cool. All right, thanks, guys.
It's hard to write and unmute at the same time.
I bet.
Just trying to make you feel better when there's no answers.
Just keep it on and just breathe real loud. Like my student today, it was like, you all right there? And they just kept breathing.
Oh, they're mouth breathers. Cool.
It's like, I'll put you on mute.
Good old window lickers.
Yeah.
Cool.
That's going to be the new kids in Seattle.
So my dog is like, she's really sick and she's got cancer and her lungs are starting to go bad. So she breathes really heavy right now. And so whenever like I call my husband and she's in the car with him, you can just hear her just and it's so sad, but also kind of funny just hearing it over the Bluetooth. We're trying to like make light of the whole situation.
Just ruined my day.
I'm so sorry. She's happy. We're
dead.
feeding her from the table like all the time now. So she's like a
Aw.
fat, happy dog.
Nice. Okay. So now we come across the derivatives of trig functions. Yeehaw. So here we have the derivative of sine, which is cosine, and the derivative of cosine, which is negative sine. So if you think in terms of slope, it's actually pretty crazy that cosine can give the slope for a sine function, and sine, well, negative sine, can give the slope for a cosine function. So this is something to think about, other than computational. But for now, all we understand is that the derivative of sine is cosine, and the derivative of cosine is negative sine, which we can start using below. So for number 11, y equals 3 sine theta plus 4 cosine theta. And to play with notation, I'll say the derivative dy over d theta. What is the derivative of 3 sine theta going to be?
Three cosine.
3 cosine theta. What is the derivative of 4 cosine theta going to be? Ah.
-4 sine theta.
That's it. -4 sine theta. Any questions on that one? Okay. Do it again. 12. Z equals A over y to the 10th plus B cosine y. So here we have to, of course, rewrite A over y to the 10th. So my rewrite is just going to be Z equals A times y to the -10 plus B cosine y. And now we'll take the derivative. And again, a play on notation. I'll say the derivative of z with respect to y, dz over dy. What is the derivative of a times y to the -10 going to be? And just treat a as any normal constant or coefficient in this case. So what would we have?
Negative NA to the power -9.
Remember, you go more negative.
To the power -11.
There you go. And then what would be the derivative of b cosine y?
Minus b cosine y.
Not
Negative.
cosine, but
I mean sine, sorry.
there you go.
Yeah, I was looking at it.
There you go. And that's perfect. Yes, we can rewrite the first term if you want to. We could also have -10a over y to 11th minus b sine y. Okay. And 13. Y equals sine theta over 2 plus c over theta. So again, we should rewrite this. And I'm going to rewrite sine theta over 2 as 1/2 sine theta plus, and c over theta, I'm going to rewrite as c times theta to the -1. Okay. And now our derivative, I'm just going to say y prime this time. What is the derivative of 1/2 sine theta?
½ cosine theta.
There you go. What is the derivative of c times theta to the -1? And again, just treat c as a coefficient.
-1.
Negative. So
Well,
this will
once-
come down and multiply that, right?
So -1c.
Times theta to the what?
-2.
There you go. Perfect. Or 1/2 cosine theta minus c over theta squared. And y'all, those are derivatives. That's it.
Woo!
That was your best lesson ever.
Shortest one, right?
Give me time to take my test tonight.
There you go. So normally I have a lot more problems on here, but since we're remote, I'm like, oh, I'll cut some out. I'm not going to keep them here for more than an hour. These are derivatives. As long as they know power rule, that's all you need in life. And of course, now the derivative of sine and cosine, which you can consider derivative identities if you wanted. But that's it. We're done.